if you recall, you're in a lecture for a class. Yeah. All right, guys. Okay, so let's get started with class today. You know, we really do start at 2:35, which is already 5 minutes after the scheduled time for this class. Oh my goodness gracious. Alright guys, right, so welcome back to 837. Like, let's see here, how many of you guys completed the last homework? Good. Alright, so your next one, you look at me like that, but you have latex, you're allowed to take that. Right, so your next homework is already out. This class is on just every 2-week kind of rotation now. So you should take a look. Unlike all the previous assignments, you already have all the material you need to do that homework. In fact, our lectures will be covering stuff for your next homework. So you should get started. Is there like something going on in the department today that I'm missing that we're all kind of chatty? Okay. Right. So yeah. So anyway, your next homework is out. You should get started. I like this homework. I feel like students don't have quite as much trouble with this one as the previous one, but I can't speak for all of you. so get started. Okay. There is no class on Tuesday. It is a holiday, Indigenous Peoples Day, I suppose. And on Thursday is your next class. What does that imply about Thursday? What happens on Thursday? Okay. If I receive, yes, no question mark. Period. There's a nano quiz on Thursday. I'm debating if you email me asking if there's a nano quiz on Thursday, or asking where the calendar is that tells you when the nano quizzes are, I may give you a 0 for that quiz. Okay? It's like, I'm so tired of getting these emails. And you laugh, but I got another one yesterday. Okay? So please don't. Alright. Are there any questions, procedural? Oh, and your course project, I promise I will write the instructions and share it by the end of this weekend. I want to revise them over previous years. And I said that, but then I didn't actually do anything. So I'm gonna take care of that, and Tao and Linda are going to ruthlessly hound me until that happens. If you send me cat pictures, I'm going to be looking at cat pictures. I'm not going to be writing your courses. Yeah, okay. All right, so if there are no procedural questions, let's get started with rendering. So this is sort of part 2 of 837, and probably the part that everybody associates with the discipline of computer graphics, right? Which is how to go from the content that we modeled, like in the previous couple lectures, right? Whether it's geometry or something deforming over time, and actually drawing it on the screen. Yeah? And that's the process called rendering. And I think you guys probably all know that intuitively, and now our job is to fill in what the algorithms look like. Right? So the story so far is that we have some pretty neat tools for modeling, and many of which you've actually implemented on your homework, right? Everything from splines to hierarchical transformations, skinning, meshes, and so on. We talked about animation, and in your next homework you'll see you can kind of procedurally generate some cool motions for a piece of cloth, and I think springs connected by particles. This also seems to be kind of a popular topic for final projects. The students kind of like implementing, like, you know, I'm excited about this physical phenomenon. Let's see if I can capture it. That's a totally fine, interesting final project. But be warned, I feel like physical simulation papers are dangerous because they're really hard to get them to actually work. But that's my experience. Right. So our next task, now that we have all this content, is to actually draw on this. So given what we call a scene description, right, like all the contents of everything you're looking at, we want to go from that to an actual array of pixel values, which I think is a pretty natural problem to talk about in graphics class. So today we're going to talk about rendering, and we're going to, in particular, define for you the most, well, one of the most basic algorithms for rendering, which is something called ray casting. By the way, so ray casting and ray tracing are very similar algorithms. I don't personally see the need to have a distinction between these two things. So if I use them interchangeably, just beware some people treat them slightly separately, and I'll point out in the slides where people see the dividing line. I don't think it's really a big deal to distinguish between these things, and certainly on your exams, quizzes and stuff, I would never be like, what's the difference between ray casting and ray tracing? Because I don't really care as long as you can draw a picture on your screen. Cool? All right. So, what is the rendering procedure? Well, really, it's all about taking a scene which could be composed of all kinds of different objects, whether it's the triangulated bunny or a teapot that consists of the sort of basic nerve surfaces. By the way, these are the two kind of basic test surfaces everybody uses in graphics, so you see them over and over and over again. And your job is to create an image, right? And so one way to kind of think about what's going on is that your image is like some imaginary screen door that's sitting in front of your camera, right? And what you're doing is for every little piece of your screen door, you're deciding on a color for that pixel. Yeah? So if you're the camera, I mean, you can already kind of see what's going to happen in a rendering algorithm, right? I'm going to take a line and draw it from the camera through the pixel and into the world and see what it runs into, and then check the color of the thing that it runs into, and that's going to be the color for the pixel. And really, rendering is as simple as that, right? I mean, there's nothing totally earth-shattering about the way that the basic rendering algorithm works. Yeah? So, and of course, depending on your basic setup, there are a lot of things that might change about the way that I've described it to you here. Whether the image plane maybe warps a little bit to get a cool camera lens effect, or maybe you have more than one ray that goes through every pixel to try and blow stuff out a little bit. And all of these are different variations of the basic technique. Yeah? So in particular, for today at least, every pixel is going to correspond to one ray, right? So in other words, your pixel occupies a little bit of space in this kind of imaginary image plane that's in front of you. I send a pixel right through, or a ray right through the center of it and see what it runs into, and that's the color that I read off on the screen. By the way, do you think that's what actually happens in most rendering? Like if you, even either video games or in kind of high-end studio stuff? No. Right? And there's a very simple reason for that, right? Which is that, I mean, you can even see it in the picture that I've drawn for you here, right? Every pixel is like a little rectangle in the world, and a rectangle can contain a lot of stuff, right? I mean, I can take this, might be a single pixel, like if I zoom out really far, and I can see some students, I can see the chairs, I can see the dark stuff on the bottom of the chair. And so remember, at the end of the day, the computer is set on one color to put in that pixel, and there's no like God-given physical rule that says it has to be the color right in the center. Yeah? And in fact, when we talk about anti-aliasing and sampling, we're going to come back to this basic assumption that there's one ray per pixel and say, well, maybe what we really want is sort of the average color inside of that little window, or maybe we want to bias it toward the center or something. Yeah? But for now, we're not going to worry about that distinction. What you'll see is that regardless, the basic algorithm is the same. It's just a question of sending more than one ray through a pixel instead of just one. Yeah? Cool. All right. And then the next step, of course, you send your ray through your pixel, it hits the bunny's nose in this case, and I want to render it. And to do that, the next calculation I have to do is involves the lighting and shading in your scene, right? So obviously the colors that you see on the bunny depends on the positions of the lights. It depends on whether or not there's a shadow or a reflection or what have you, and all these things basically affect what you're going to see. Yeah. I think all this stuff's totally reasonable. I don't think you're missing. Okay. Right, so a couple vocabulary words that you probably already know. Rendering refers to the entire process of going from a description of a scene to one color per pixel. Typically a pixel we kind of think of as corresponding to one ray or a little bundle of rays that go out into the world. And what they're sensing is the visible point. Right? So for instance, looking at Magnus, and behind him is, scared? Behind him is Raphael, right? If I did my algorithm incorrectly, maybe just because of I store my list of students in reverse alphabetical order, I happen to notice that the ray eventually hits Raphael first. Doesn't mean that's the color I should choose. I have to also do a little bit of calculation to figure out occlusion, right? Which one's actually visible from the position of the camera. And there are a lot of names for this. Essentially, we call it the hidden surface problem for very obvious reasons. And in the ray casting algorithm, this is going to be very easy to resolve. In rasterization, which we'll talk about later in this course, it'll be much more difficult. Right, so the basic difference here is in ray casting, it's exactly what it sounds like. I send out a ray into the world and I just compute the closest thing to it. In rasterization, I take a list of everything in the world and I draw them one at a time. Right? And so in an algorithm like that, occlusion is going to be a little bit more of a pain because it might be that I draw something and it's already kind of behind whatever I already drawn. So that's where things like the Z buffer come into play. So anyway, these are the two basic algorithms, ray casting and rasterization. Obviously, we're going to fill in a lot of detail about these in the coming lecture. Okay, so our plan for today is roughly to talk about the basics of the ray casting algorithm, talk about how you deal with your camera and computing rays and so on. And then we're going to give you your first two rendered primitives, which are ridiculously simple. We're going to tell you how to render a plane and a sphere. And indeed, if you look at the early computer graphics work, you'll notice that there's a lot of planes and spheres because that's what people could do the math for. Obviously, we're all grown-ups here, so we're going to do a lot more than that in the coming lectures. But this is a good starting point to just get an idea of what these calculations look like. Yeah? Okay. So the rate casting algorithm, which I already described for you more, is roughly looks like what I'm giving you here. So there's going to be a loop, an outer loop over every pixel, right? So essentially for every pixel, I'm going to determine what the color is. And what am I going to do? I'm going to construct a ray from the eye through the pixel into the world, and then I'm going to iterate over all the objects in my scene and say, okay, does the ray hit the object at all? If it doesn't, then like it's just irrelevant. If it does, and it's closer than the object I've already seen, then make that be the thing that I'm about to render. Right? So after I go through everything in my scene, I can find the closest guy, and I keep it. And then what do I have to do? I have to do shading, right? I have to do some calculation involving the light to see what color I actually put in that pixel. Yeah? By the way, remember the rasterization algorithm, roughly all it does is takes these two for loops and swaps which one comes first. Right? So in rasterization, you would iterate over every object and render that object, as opposed to in ray casting, where you can iterate over every pixel and just find the closest one. So that's the basic difference. So ray tracing is very CPU intensive, rasterization is very GPU intensive. We'll come back to that. By the way, one thing to notice, I keep saying in this class that a lot of the early work in parallelism and sort of high performance computing came out of the computer graphics world. And if you take a look at this very simple algorithm here, you can see why. Right? That essentially, take a look at that outer for loop over every pixel. Does the calculation for like pixel 17 have anything to do with the calculation for pixel 25? No, right? So if I have a computer with a million processors, what can I do? I can just assign every processor a different pixel and have it work away to compute that pixel's color, and all of these things can happen in parallel. Yeah? So this is arguably the simplest way to speed up your rendering code. By the way, if you look at this little piece of pseudocode, does anybody have ideas for like other ways I might be able to speed this algorithm up?
You could go the other way. Like if you know the objects, you could try to trace them to the screen.
Okay, so you could rasterize instead of ray trace, but even within the ray tracing algorithm, what are some ideas for how to make it faster? Yes.
Order your objects so that if the intersection would happen as early as possible and you just discount anything.
Sure, so you could try to essentially get rid of objects as quickly as possible. Any other ideas? No.
Use some data structure for collision detection.
Use some data structure for collision detection. That's an excellent idea. So remember, in fact, it really is the same data structure that you might use for like, I'm making a driving video game and I want to not run into walls. Right? Exactly the same issue happens here, right? I need to figure out the first wall that my ray is going to run into. Right? And so for instance, it might be a really complicated calculation to figure out if a ray is going to run into a bunny. Yeah? But let's say I put a giant box around the bunny and the ray doesn't touch that. Right? Well, then I don't need to recurse inside of that box and check every triangle of the bunny. So that's going to be sort of the basic technique for making these algorithms faster. So do things like hierarchical modeling and say like, well, if I have a bounding box around an object and my ray doesn't even touch that box, then I can discount that and not do all these intersection calculations that I can do. One of many techniques. And there are many other ones you guys should think about. There's really cool ways to make ray tracing fast. But not super fast. Super fast stuff is still a challenge. Okay. So once you figure out what thing your ray hits into, of course you have to do some shading calculations, and we are going to return to this later in this class and talk about different shading models. Typically the information that you need to do shading, at least if it's just a function of your position on the surface, will be at least the surface normal, the direction, like where's the light that you're trying to render, and where's your eyeball. Yeah? Obviously all three of these pieces of information are relevant, right? If I take an object and I point it toward a light or point it away, it gets darker or lighter. Yeah? If I move and I look at a mirror, things move with me, so clearly my position matters, and so on. Yeah? By the way, can you guys give me an example where that information is not enough? So let's say I try to render a marble statue. So what happens in a marble statue? Well, it turns out this is a great example of what we call subsurface scattering. That you have light that comes into the marble statue, it bounces around in the interior of the marble statue, and then it comes back out to your eye. Yeah? And what that means is that if I just render a point on the marble statue, or a point on Linda, because skin is another great example, that seems to be why she's pointing to herself, then both of these are good examples where the stuff underneath the surface matters a lot. So it's not enough to just know where you hit into the surface and where the light is. Yeah? And so this is sort of the beginning of all kinds of really complicated rendering models that are really critical for capturing the world in a nice way. Yes?
If you had like a translucent material, once you collided with it, couldn't you like attach a weight and then like recursively like shoot another ray inside the object?
Absolutely. Yeah, and that's roughly the way a lot of surface scattering methods work. Right? That essentially you figure out what thing you ran into, and now you have to scatter a bunch of rays in the interior of the object you ran into to kind of figure out where the light's coming from. One of the big issues, of course, is that really you're getting this giant integral over every possible direction, and it's not clear how many of those rays you have to send out before you have a good sample. These are just things to think about. I'm not giving you an answer right now. These are just reasons why this can become really challenging. Yes?
What's the behavior you need the normal for?
The behavior you need the normal for. Yeah, absolutely. Let's see. Let's say that I'm rendering the sunset. Here's the sun, and I'm looking here. I am, and I'm looking this way. Yeah. What happens when the sun's down here? Nothing. Like the ground doesn't reflect the sun at all. Yeah. And similarly, when it's directly overhead, it matters quite a bit. Yeah. And so roughly, the way to think about it is in the extreme. Well, if the light is coming in parallel to the surface you're trying to render, it doesn't actually bounce off it. You don't actually see anything. Right? The basic model for this, does anybody know the basic model for shading that makes use of the normal? Any of this thing? What's that? Snell's law is an example of a thing that uses the normal, for sure. But another one is called inversion shading, which is going to be the first shading model we cover, which says, so here's a surface, here's this normal vector and hat, here's the light, and that the shading that you see at this point has to do with the dot product between the vector toward the light and the vector toward the normal. Right? So in other words, when the normal and the light are aligned, it's the brightest, and as it goes away, it drops off. And that's exactly what you're seeing in this diffuse sphere here. Right? So as the light moves around, the shading changes. You can see the dependence on the normal, right? It drops off depending. Great question. Okay. Yeah, and so anyway, we're going to talk a lot more about shading later in this class and go over different types of materials, how you might construct a physical device to measure materials, and so on. These are some fun topics. Okay. I promised you I'd tell you the difference between ray casting and ray tracing, and here you are. So let's say that I want to render the circle. Yeah? So it's always hard to draw a camera and a scene into it, but bear with me. Yeah? So let's say I render the circle, so I draw a ray toward the circle, and I want to, that's clearly the closest thing that hits into my ray. I want to shade it, so what do? I see the light's up here, the camera's over here, I take the dot product, and now I have a circle. What went wrong? Well, there was a big box in between the circle and the light, yeah? So it didn't actually receive light. Yeah? So in the ray tracing algorithm, what you would do is you'd say, okay, well I just hit into the circle, now I'm going to draw a ray from where I hit toward the light, and I'm only going to render that light if nothing is in between. Because otherwise, essentially, the light is occluded. So that's the ray tracing algorithm. So that after I figure out the first thing that I hit, my job here isn't done. I still have to send out what we'll call secondary rays to determine things like shadows and reflecting and so on. And so it's a recursive algorithm. But the nice thing is that once you've implemented ray casting, it's very simple to extend your code to ray tracing, right? So if you write a piece of code that just says, given an arbitrary ray, what's the first thing that it runs into? That's the same piece of code you're going to need to send out what we'll call a shadow ray. That makes sense? Okay. And so camera ray is a ray from the camera into the scene, and then what we'll call a shadow ray is this other guy which draws some light to the shadow. Okay. And so these things are called secondary rays. They can be used, for instance, to check reflection, to check shadows, refraction, all this kind of stuff. So we'll talk about a couple of the basic physical rules that govern this kind of things. Okay. Secondary rays are not just used for like checking if there's shadows or bouncing light off of things, but they can also be used pretty frequently in cases where you're lighting stuff and it's kind of diffuse or like kind of, like the light around us, the shadows that we cast tend not to have sharp edges, right? But everything I've described for you so far is very much a sharp edge, right? I draw a line toward the light bulb and either it hits or didn't, you know? And so there are a lot of rendering techniques that we'll call indirect illumination, which is essentially where the world around us is fuzzy and glowy and so on, right? And these can capture all kinds of cool things, whether they're having soft shadows, having reflections, refraction, and also things like caustics, right, where your light kind of comes off the ceiling, focuses through this object, and then hits the room. So you have this little light spot there, or even secondary reflectance of light, like maybe you get a little bit of blue glow off of the wall that bounces onto the floor. So all of these basic things wouldn't be accounted for in the simplest ray tracing algorithm, but are simple extensions. And one of the really cool things, by the way, and actually one of the easiest homeworks to get extra credit on, I think, is your next homework, which will be on implementing a ray tracer. Because essentially choosing any one of these phenomena and adding it to your code tends to be very simple if you modularize your code correctly, right? That it's just a question of casting some other ray and doing the same calculation. Yeah. Okay. Right. So ray tracing can account for all kinds of cool behavior here, and we'll talk about in the coming weeks how to capture all of these different effects. Okay. But for now, we're going to start basic. So, if we're going to write a ray tracer, what do we need to do? We need to represent a ray. Yeah? And so that's our first question. How do I store a ray on the computer? Any ideas? Before yeah? Yeah, a vector and a point, right? So I could store the location of your eye, and I can store the direction where it's pointing. Completely reasonable way to store a ray on the computer. Unlike lines, a ray really does have a base point. Like think about the ray tracing algorithm, right? If the closest object to me actually has negative distance, like it's behind me, I probably shouldn't count that in my calculation. Yeah. So the sign actually does matter. But just like we suggest, probably the easiest thing to do is to store a pair of things, right? One location in space, a point, and a direction, and then I can get any point along this parametric ray by doing your origin plus any arbitrary positive t times your direction. By the way, a source of bugs often in ray tracing is how to handle t equals 0. There's no right answer here, and in your code for the assignment, you'll see that some tricky things can happen if you don't handle that case right. What I'd recommend is saying if you're, just choose some positive epsilon, and if your ray doesn't hit something by that epsilon, just ignore it. But we'll come back to that later. By the way, is this representation of an origin plus a direction unique? No, right? If I took that direction vector and multiplied it by 7, it would still give me the same ray as a geometric map, right? We are going to give it a sign, so we're going to say minus the direction does define the ray because it points the other way. Yeah? So typically the convention is to think of the direction like a unit vector, and I would encourage you in your code to just take all vectors like this and just keep dividing them by the length because it can work. And it'll simplify some calculations later. You can save yourself some square roots by just saying, well, the direction doesn't have to be a unit vector, and maybe that's okay. Okay. Right. So the ray casting problem step, like the really basic thing your ray caster has to solve is to find the smallest t greater than 0. Notice that phrase, the smallest positive t, such that p of t hits a surface in the scene. Right? So it's not just the smallest t, because that can be behind you. Right? Yeah. And of course, ray tracing has a very, very long history, and I encourage you guys to go Wikipedia read a little bit about this. So, for instance, in fact, all the way in the 16th century, I kind of appreciate this what, Jura guy? I don't speak German. Where he really actually made ray tracing, like physically. So like here, if you want to make a painting of a scene, maybe you actually take a piece of string and like kind of, put it through the pixel into the world and read out some color. It's like a very engineering heavy way to represent a scene on an image. But if I recall, it actually was one of the earliest ways that people sort of got perspective when they were drawing scenes in paintings. Right? So at about the same time, all of a sudden, like if you look at these old Renaissance, everything kind of looks like they're flattened up against the plane of the painting. And suddenly, with this kind of technology, people realized really clearly that isn't the way the world works. It seems obvious now, but of course back then maybe not so much. Sorry, here's another picture. Here, I guess he's doing it behind him, so he has this kind of mirror device looking to see. I won't even attempt to explain this because I'm showing it wrong. It's kind of cool stuff. Be glad that you have computers to do this for you. So our next task for today is to figure out how to intersect rays with stuff in our scene, and to talk about how to deal with your camera and all these kind of basic things. All right. So remember that again, our basic ray casting algorithm. The very first thing you have to do is to construct a ray from the eye through the pixel you care about, and that's a very simple thing to do. Okay? And so in our first model for this, we're going to use what we call the pinhole camera. Have we ever heard of pinhole camera before? That's exactly what it sounds like if you haven't, right? So pinhole camera means that I'm thinking of I'm imaging my scene over here inside of some box, and I punch an itty bitty little hole into my box. And the reason for doing that is that it restricts the rays of light coming into the box, through the box, and onto the image plane behind it as having to go through essentially one point. You know? Which is, if you think about it, is kind of the model that we have, right? So this is kind of like having your eye placed here. Of course, in the pinhole camera model, the rays go through the pinhole here. They keep going. You know? So, in particular, what happens to your image when you use a pinhole camera? Flips over. Yeah? See that? Here's an upside down teapot. And the reason for that is take a look at these two rays, right? They reverse order when they go through the hole. Yeah? Of course, pinhole cameras are not physically realizable in the world, right? I mean, the idea of having an infinitesimally small hole through which you receive all of your light is not really an accurate one. Of course, your eye does a reasonable job of approximating that. But even in that case, you have things like lens aberration and the fact that you have a big hole in your eye taking in light. That means that really the scene that you're getting is not just all the rays through a single point, which is roughly the model that we've been drawing so far, but also maybe some rays that are like perturbed a little bit. But if you think about the ray tracing, it's not so difficult to simulate that effect, right? What would you do? You just send more rays. Okay? That's the really nice thing about this. So this is what we call sort of the simplest version of geometric optics, and it doesn't include things like depth of field. Yeah. So if you like all close one eye and you like look at your hand right in front of you, right? So there's no perspective, so you're only going to see one image of the world. But if you look at your hand, all the people behind you, I can tell you, I'm experiencing it right now, are fuzzy. Yeah. And similarly, if you hold up your hand and you're looking at the people behind you, your hand's fuzzy. Yeah. And the only way that depth of field effect can happen is based on the fact that the lens of your eye isn't a pinhole camera. Yeah?
How would you implement that, like on a computer?
How would you implement depth of field? We'll actually talk about that in quite some detail in a couple of lectures. Yeah. Great question. Okay. So here's right, all these things, I think in the 1500s were a big focus where people were just starting to understand that light isn't like some weird chemical that's moving through the world, but really does have interesting properties that are systematic in study. So here's an image of a pinhole camera all the way from 1545. And this was from, I think, an astronomer who was using a pinhole camera to study the solar eclipse, right? And of course, as you guys may have experienced a couple weeks ago, you probably don't want a giant lens taking it away to study the object, because you're not going to see it ever again. Right. And in fact, this is sort of a popular idea. So here, this is another name for the pinhole camera. It's the camera obscura. I think roughly the reason for this is in order to actually see this image, you need a really dark room. The reason being that, I mean, essentially, by having a pinhole, I've cut out most of the light of the world, right? So in practice, you're going to get a very, very weak signal that comes through that pinhole to image, right? So if you wanted to actually do this in real life, to have a pinhole camera, you probably have a very dark room to see with your image. Okay. And this term actually, I think, was coined by Kepler, which would have been what? Also in the 1500s. So it was a big time for this kind of stuff. Okay. And indeed, today, we don't really need pinhole cameras anymore, but there is a kind of a cool artistic effect. So you can see here, this guy, I think is, that's the Capitol building, right? And he's sort of showing you can actually image it against the wall of somebody's bedroom if you set up your pinhole camera just right and have a very slow exposure for your camera that takes in photos. Kind of surprising. Right. So the reason that we like the pinhole camera is it gives you a very simple model for how to figure out where your rays go in lighting, and it really is approximately what you experience, right? Like especially if you look at kind of far field images, you don't really notice that depth of field effect a whole lot, right? That fuzziness, so that's what we're trying to approximate today. Do notice that you know, yet another way to think about the pinhole camera is that there's like a lot of different image planes that are all moving out of your eye, right? That are kind of foliated or like kind of bounded by these two lines here. Right, so the farther you go out, the bigger the image plane gets. And so when what we see, you know, what we might perceive as very large might be very small relative to what we see in the image. So for instance, if I hold my hand here, obviously my hand is taking up a large part of what I can see right now, even though, you know, the students in the class are much larger, for the most part. Okay, right, so yeah, so if we want to describe a camera, what do we need to do? Well, we probably want to know where the camera is, and we'll call that point E for eye. And in addition, we need a frame for our camera, right? We need to figure out what direction your head is pointing and where you're looking. Yeah? And so, in general, the typical way to do this is to have an orthogonal basis where you have an up vector, which we'll call V. This is like, you know, approximately where my bald spot is pointing. You'll have a sideways,